So you have discrete probability distributions, and then we'll actually talk about binomial probability distribution in section 6.2. So a lot of your definitions and everything, are going to be the same, but remember in chapter 1 we had discussed random variable. So basically we're saying a random variable is a variable whose values are determined by chance. So that means we have no control over them. So you can classify your random variable into two different types of variables, either discrete or continuous. Now remember, when we are talking about discrete variables, we are basically saying they can be finite or an infinite number of values that can be counted. So any value that can be counted would classify as a discrete variable, and then any values that can assume values in the interval, in between any given two values, are what we call as continuous random variables. So we're saying continuous random variables are obtained from data that can be measured rather than counted. So anything that can be counted, and in this case, I would say think about, the number of students in a class, how many kids are there in a family. Those are numbers that can be counted. When we're talking about values that can be measured, you measure temperature, you measure somebody's height or weight. Because even though, let's say about a height, we may say a person is, 6 feet, 1 inch tall, that restriction is coming from the instrument you are using to measure them. Because technically the person could be 6 feet, 0.95 inches tall, right? But we're just going to say, he's 6'1" or something like that. So a lot of times the measurement can assume values, in between two variables. So, 6 feet to 6.1 inches, they can be anywhere in between. But just depending on what you are using to measure can, restrict how our answers get rounded. So when we talk about a discrete probability distribution, this is kind of what you want to think about. So we are starting out with a probability experiment where we are tossing 3 coins. So we're basically saying if you are tossing 3 coins, our sample space is going to end up looking like this, where all 3 of the coins can land on the tail. You can have 2 tails, 1 head, 2 tails, 1 head, just in different order, 2 tails, 1 head. You can see in these 3 outcomes, we have 2 heads and 1 tail, but just depending on, which coin landed on which side. Or all 3 of the coins can land on 3 heads. So technically, there's only one outcome where we have no heads. There is 3 different outcomes where we can get 1 head. So, 2 tails, 1 head, 2 tails, 1 head. We can get 3 outcomes where we have a total of 2 heads. So you can again see what those outcomes will be. And there will be just one exact outcome where we get 3 heads. So if our X value was going to be, how many heads, 0 heads, 1 head, 2 head, or 3 heads, the probability based on that would be, and you can kind of see that over here, X is representing the number of heads. So there's only one outcome where you had, 0 heads. So that is going to be a probability of 1 out of 8. There are 3 outcomes where you had exactly 1 head. So that's a probability of 3 out of 8. There are 3 outcomes where we had exactly 2 heads, and that's again going to be 3 out of 8 as our probability. And just 1 single outcome where we had all 3 heads, and that's going to be 1 out of 8. Now remember, these probabilities are coming from the fact that in our sample space, we have a total of 8 outcomes. So that's 1 out of 8 for 3 tails, 1 out of 8 for 3 heads. And then you can see this 1 out of 8 for each one of these outcomes. But since we are interested in, how many total outcomes had just 1 single head, well, that's a total of 3 outcomes that had 1 head, and a total of 3 outcomes that had 2 heads. So based on that, we are able to come up with this probability distribution. And that's what they are talking about here. Your discrete probability distribution consists of values of a random variable that can, that it can assume, and their corresponding probabilities. So what will the probabilities be for those random variables? Now your random variable here is X. And in this experiment, the X represented how many heads would we get if we toss 3 coins. And they are saying these probabilities can be determined theoretically or by observation. And, it would, of course, depend on the experiment you are doing. And then here, they're just giving you a step-by-step breakdown of how to construct a probability distribution. So using, let's look at this example here. I like this one. So this one is talking about a convenience stores sells AA batteries. So it's got 2 batteries per package, 4 batteries per package, 6 per package, and 8 per package. So these are the different types of battery packs they have. Now they're telling us the store is selling 5 of these 2 packs, 10 of the 10 packs, 8 of the 6 packs, and 2 of the 8 packs over the weekend. And based on this, they want us to construct our probability distribution. So the first thing we would have to do is define what our random variable X is going to be. And you can define this based on how many batteries are going to be in a package. So you have a package which has 2 batteries, a package with 4, a package with 6, and a package with 8. So that is how many batteries does each of the pack have. And then based on how many packs they sold, we can come up with the probability distribution. The first thing you would have to do is calculate the total number of packages they sold. So of course you've got 8, 2, which adds up to 10, 10 plus 10 is 20, 20 plus 5 is 25. So you are looking at a total of 25 packs they sold. So when you want to calculate the probability for each one of these packs, well, we sold 5 of these 2 packs. So that's going to be 5 out of 25, reduce that fraction down. We sold 10 of the 4 packs, so that's 10 out of 25. We sold 8 of the 6 packs, so that's 8 out of 25. And we only sold 2 of the 8 packs, so that's 2 out of 25. And you can see based on that, they calculated our probabilities, and then they are converting the probabilities into decimals. So you can convert them to decimals, or you can, leave them as reduced fractions. So whatever, helps you out. This one will not break down anymore. So these would be your reduced fractions, or you can do decimals. So some of the things you have to be careful about when you're working with probability distributions, all of these probabilities have to add up to a total of 1. So even if you have them as fractions like we did over here, this has to total a total of 1. So if you think about it, and we talked about adding fractions last time. So you can see each one of our denominators is 8. So if we just go ahead and add these fractions together, well, you're just adding the numerators. The denominator will stay the same. So you've got 3 plus 3, which is 6, plus 1 is 7, plus 1 is 8. And you can see that adds up to 8 out of 8, which will be a total of 1. If you add up these decimal numbers, 0.20 plus 0.40 is 0.60 or 60. If we just keep it as whole numbers for now, so that's 60. Plus 30 will bring it up to 90. And then 8 plus 2 will give you 10. So 90 plus 10 will give you 100, which again, as a decimal comes out to be 1. So your probabilities all have to add up to 1. And that is what this first one is talking about. The sum of probability of all events in your sample space must equal 1. Each probability, so for each event, your probability in the sample space has to be either between 0 and 1 or equal to 0 and equal to 1. So the idea is each one of these probabilities has to be a number between 0 and 1. It can also be 0 or it can also be 1, as long as all of those probabilities, when you add together, still adds up to 1. So, you cannot have the probability, let's say, of this first outcome be 1 over here, this outcome be 1, this outcome here be 0.5, and this one maybe be 0.25. Because when I add up all of these, this is going to be a number greater than 1. So you cannot have that either, because all of them have to still add up to a total of 1. So you know what that means, if you think about it logically, let's say if this guy here had a probability of 1, that means all of the others would have to have a probability of 0, so that when I added everything, it would still come out to be 1. And so that's why we say your probabilities can be between, or they can be equal to 0 and 1. And it will again depend on what example you are looking at to be able to, see what kind of probabilities come up to. So you will see there's actually an example over here, which is asking us to determine if these are actually probability distributions or not. And so that's going to be one of the things you will be looking for is, are all of these probabilities between 0 and 1 or equal to 0 and 1? And when you add them together, what does their total come out to be? So in this case, you will see we've got 3 plus 4, which is 7. 7 plus 1 will be 8. 8 plus 2 will be 10. And 10 plus 1 will be 11. So this is actually coming out to be a total of 1.1. And you will see this is a number larger than 1. So that is why this first one is not a probability distribution. Even though in setup and everything, it looks very much like a probability distribution, but of course, our numbers are not adding up. Now, again, these are all between 0 and 1, because you can see these are proper fractions. But then when you add them together, will this total come out to be 1 or not? Same thing over here. All of these numbers are 1/4, 1/4, 1/4. So again, all of those fractions are proper fractions, which means you're between 0 and 1. And then, of course, when I add them together, will they add up to 1? So where these guys, meet these two requirements that we have, you've got a probability distribution, which is what these guys are. Yes, they are probability distribution. But look at that last one. You have a negative number over here. Now, remember, your probabilities have to be between 0 and 1 or including 0 and 1. So you cannot have a probability, because how can we say there's a negative 0.6 chance that you will get the number 3, or whatever the result might be? You cannot have negative probabilities. So again, this is not a probability distribution. So you don't even have to worry about adding those numbers together, because you just cannot have a negative probability. So this is something you always have to be careful about when you're working with probability distributions. But that's basically how you come up with these table. You define what your X value is going to be, and then based on that, come up with the probabilities. And remember, this is what you guys are doing with that flip a coin assignment, because remember, you are doing your experiment. You're doing 3 experiments, and each one of them has a trial of 10 times. So based on that, you are coming up with, how many heads do you come up with, which your numbers will go from 0 to 10, depending on what your coin flip gives you. So that's where this whole idea is coming from. And then, you have to calculate your probability based on that. Then we kind of get into how do we calculate our mean, variance, and standard deviation for, these probability distributions. Now, this is what we are kind of used to, what we saw back in chapter 3, how to calculate sample mean and population mean. But, when we get into probability distributions, your calculation actually changes a little bit. And I guess they don't have the 3 coin flips over here, but let's take a look at this example here. So here we are talking about tossing 2 coins. So we're tossing 2 coins, and these will be our outcomes in our sample space. So again, you can see based on how many heads we are talking about. If you're talking about two heads, then that is going to be a probability of 1/4. If we are talking about getting one single head, well, that's these two outcomes. So the number of heads can be 1, but you will have 2 out of 4, or basically a probability of 1/2. If you have 0 heads, which will be, this outcome over here, well, that's again going to be 1 out of 4. So when you calculate the mean for a probability distribution like this, you actually have to multiply the value of your random variable with its probability. So that means you are multiplying 2 times 1/4, which is where this guy is coming from. We are multiplying 1 times 1/2, and that's just your reduced fraction. You can obviously do 1 times 2/4 if you wanted to do that, which is where this guy is coming from. And then our last outcome was 0 times 1/4, which is where this is coming from. So when you simplify them, add all those numbers together, this ends up giving us a average or a mean of 1 in this case. So we would say our average of number of heads would be, 1. And that's what this formula here is talking about. So multiply the random variable value with the probability and then add them all together, which is what that summation is doing. And then, you've got a couple other examples over here. They're talking about tossing a die based on the different outcomes and the probabilities. You can kind of see using that same formula, we end up getting 3.5 or 3.5 as our mean over here. So in this case, this is more of a theoretical answer because you're not really going to land on a 3.5, when you toss a die, but it's basically saying, that's what the average of all of your outcomes multiplied with its probability comes out to be. So you can see we're saying this is more of a theoretical average and not something you will actually experience if you keep tossing the coin, a die in this case. So, some of this kind of gets down into you're not really going to get that answer in reality, but it's more of, that theoretical aspect to it. So you've got a couple different examples here showing you how to calculate that mean. This was talking about, looking at the sample space for a family that has 4 children. So how many girls they end up with. So, if they have all 4 boys, well, then that means they have 0 girls. And that's 1 out of a total of 16 outcomes. How many of them will have, just 1 girl. And so you go and find all the outcomes where you see just 1 girl, as an option. So you go and find all of those outcomes. And that's 4 out of 16 with just 1 girl in it. So based on that, we come up with our probability distribution. And then, like I said, multiply each outcome with its, or each event with its probability. So 0 times 1/16, 1 times 4/16, 2 times 6/16, 3 times 4/16, 4 times 1/16. So do all the multiplications first, and then go ahead and add those numbers. And you can see we're saying on an average, if you have a family with 4 children, 2 of them will be girls. So we are saying that's your mean number of girls that the family will have. Oh, there's your tossing those 3 coins. So you can see this average then comes out to be 1.5 or 1.5. So, again, we know we're not going to get exactly 1.5 heads. So this is another one of those examples where you're going to get a theoretical answer instead of a practical one. Here's our example on the battery pack example that we looked at. So using those probability distribution values, again, you can see we are saying the mean number of batteries that they sold was 4.56. So again, more of a theoretical answer that you come up with. So this is your formula for calculating the mean for these discrete probability distributions. And in that same way, you actually have your variance and standard deviation formula. So you can see this is our variance formula over here. And then when you take a square root on that number, you get your standard deviation. So they're using, that same idea of if you were rolling a die and this is what our mean came out to be, then based on that, using this formula, this is where you take x squared multiplied by the probability. So, in the mean calculation, you were just doing x times p of x. Here, for variance, you are doing x squared times p of x. So multiply the x squared, each of these values will be squared. Multiply with their probabilities. And then add those two together. So you can see 1 squared times 1/16, 2 squared times 1/16, 3 squared times 1/16. We're doing this for each of these outcomes. Then we add them together, and that's the first part of our formula over here. Once you get that total, from that you are subtracting the square of your mean value. So our mean is 3.5, so you are subtracting the square of 3.5. So breaking that down, subtracting those two values will end up giving us the variance. And in this case, you can see it comes out to be 2.917. Take the square root on that, and that gives us our standard deviation. So in this case, since you're looking at a discrete probability distribution, we cannot use those same formulas that you saw in chapter 3. So we have to modify those formulas to accommodate, our discrete probability distributions over here. I guess they don't have the example with the 3 coins being tossed, but another one of these examples that I really liked was this one over here. This is talking about, how long do people have to hold the phone if they call into a talk show or radio. So they're saying a talk radio station has 4 telephone lines. If the host is unable to talk, during a commercial, when they're not on air, or is talking to a person, the other callers are placed on hold. So when all lines are in use, others who are trying to call in will, of course, get a busy signal, if all 4 of those lines are in use. So here we want to know the probability that 0, 1, 2, 3, or 4 people will get through is shown in the probability distribution. So, since they have 4 lines at the same time, you can let at a max of 4 people, through. So they want to find the variance and the standard deviation. And then they are asking the question, should the station have considered getting more phone lines installed? So if, people are having to wait for a longer time because all these 4 lines are occupied, should they add more telephone lines? So that's kind of what the question is. So they're giving us the probability distribution. What are the chances that 0 people get through? So that's 0.18. 1 person gets through. 0.34, 2 people get through. 0.23. 3 people get through, so they get hold of someone on the line. 0.21, and 4 people get through is 0.04. So the first thing we would do is, of course, find the mean, since we need that for our variance and standard deviation calculation. So multiply each of the event value with the probability. So 0 times 0.18, 1 times 0.34, all the way to the end, 4 times 0.04. Add all those values together, and we have our mean, 1.59. For the variance calculation, remember you do x squared times p of x. So that's 0 squared times 0.18, 1 squared times 0.34, again, all the way to the end. Add all of these numbers together. So that's the first part of our formula. Once you get that total, from that you are subtracting the square of the mean. So that's the 1.59 square. And you can see when we do the first part, x squared times px, and add them together, that comes out to be 3.79 as our total. From the 1.59 squared, that's coming out to be the 2.528. Subtract the 2 numbers together, and you get your variance of 1.262. So that's our variance. Take a square root on that, and this is our standard deviation, 1.123. So what this is telling us is basically the mean number of people calling at any one time is 1.59. So, again, obviously we know there cannot be a 1.59 person calling, but we're saying on an average, that's how many people are calling. And then your standard deviation of 1.123 is basically telling you that if you take two standard deviations, so you take 1.59 and then go two standard deviations away from it, so you've got your 1.23, and they actually are showing you this calculation here. We are saying approximately, you can have a maximum of 3.836 people who are being accommodated. And that means, they have 4 lines. They can accommodate 4 people at one time. So they are really not that many people who are waiting, outside of these 4 lines. So they're saying very few callers would get a busy signal. At least 75% of the callers would get through, or they would be put on hold. And, this is, of course, using Chebyshev's theorem, because we don't know if this is a bell-shaped curve or if it's one of those other shaped distributions. So from Chebyshev's theorem, we know that if you are 2 standard deviations above the mean and 2 standard deviations below the mean, you are within 75% of your data distribution. So if you remember, your mean would be somewhere over here. This would be mean plus 1 standard deviation, mean minus 1 standard deviation, and then you would go mean plus 2 standard deviations and mean minus 2 standard deviations. And normally we also go out to 3. So mean plus 3 standard deviations and mean minus 3 standard deviations. So within the first 2 standard deviations above and below the mean is 75% of your data values. And this is using Chebyshev's theorem. Within 3 standard deviations of your mean, you are looking at approximately, I know it's 88.89 or something like that. So approximately 89% of your data value. So if you go 2 standard deviations above the mean, you can see with that calculation, it comes out to be 3.836. So even rounded up, that's 4 people. So we are saying 75% of the people calling in, will either get through or they will be put on hold. So there is no reason for this talk show or the radio station to add more telephone lines. And so that's kind of what, you are using this discrete probability distribution to kind of help, solve some of these problems. So you can see these guys are doing good. They are, obviously at this time, they don't need to add any more telephone lines. You've got other examples over here. This was just talking about, a box containing balls, and then depending on how many balls were selected, you can kind of see what this result comes out to be. So just another example for you to go through. So this was more in generic terms of being a discrete probability distribution and what that would end up looking like. So that's one thing to consider. But then this is again kind of what you guys are doing in your flip a coin assignment that's due on Wednesday. Is, we're specifically talking about a binomial distribution. So as I had kind of talked about a little bit last time, when we are talking about a binomial experiment, we're talking about following these 4 requirements. You have to satisfy these 4 requirements for it to be considered a binomial experiment, and then for us to do a binomial probability distribution. So you must have a fixed number of trials. And remember, for your flip the coin assignment, since you flip the coin 10 times for each experiment, that's your fixed number of trials. You're doing this 10 times. Each trial can only have 2 outcomes, or outcomes that can be reduced to, just 2 outcomes. These outcomes are considered as success or failure. So in our flip a coin assignment, we were interested in how many heads did you end up getting, right? So your outcome would be your coin lands on a head or a tail, right? So that by default is two outcomes. But if we had talked about what if, let's talk about a multiple choice test. What if you have a question with four options, right? So we know one of them is going to be the right answer, and then the other three are going to be the wrong answer. So we can say those are your two outcomes. You either have the right answer or you don't have the right answer. So that can be reduced down to two outcomes. So that's kind of what they're talking about, is, reducing it down to two outcomes, thinking of it as a success or failure. Think about if you are, tossing a die. So you have the options of 1 through 6, which face it lands on. So we can say, if we are interested in looking only for 5, so we can say it either lands on a 5 or it does not land on a 5. So we don't care if it landed on 1 or 3 or 6 or 2. So like we said, if we're only interested in how many times it's landed on a 5, we can say you have a 5, which would be our success. If it does not land on a 5, we would say all of those are failures. So that's kind of how you can think about that option 2. Then they are saying the outcomes of each trial must be independent of one another. So this is where, every time you flip a coin or toss a die, it should have no effect the next time you do it. So all your trials have to be independent. And this is actually one of those examples where I would say, think about if you have a deck of cards, you shuffle your cards and pull a card out, right? If you don't put that card back in to the deck, then you do not have independent events, which means one trial will affect the next trial. So we would not meet that requirement for option number 3. But if you shuffle a deck, pull a card out, look at it, write down whatever that card is, and put the card back into your deck, reshuffle, and then pull another card out, those would be independent events. So those would be where your trials would be independent. But if you pick the card and don't put it back into the deck, that's when they're not independent. Okay, so that's what they're talking about. Make sure each trial is independent. So each of the outcomes would be independent of one another. And then the last one, we are saying the probability of success must also remain the same for each trial. So this would again be the same thing. If your events are going to be independent, then your probability will also remain the same for each outcome. So same thing with deck of cards. If you take that card out and don't put it back in, you will change the probability of success. But if you put the card back in, and keep doing that for each experiment, for each trial, then your probability of success will remain the same. So in your flip the coin assignment, we made sure that because the way that experiment is designed, you are meeting all 4 of these requirements for a binomial experiment. So here they were talking about, just to give you an idea, if you can recognize if it's a binomial experiment or not. Let's hide those answers for now. So we are saying part A is selecting 20 university students and recording their rank. Decide whether each experiment is a binomial experiment or not. And if it's not, give the reason why. So I know some of you may have looked at the answer, but think about this. 20 university students and recording their class rank. Could this be broken down into those 4 requirements? And can we say, yes, it's a binomial experiment or not? Because, class rank, we're talking about them being freshmen, sophomore, junior, senior. You can, for that matter, have graduate students and, that kind of thing.
Class ranking doesn't drop down to 2 results.
It does not drop down to 2 results. Yeah, because, class rank by the statement means, they will be different. They will be at different places. So it would not be a binomial experiment. So we are saying, no, it's not. Very good. selecting 20 students from a university and recording their gender. And this question kind of comes down to, are you just looking at gender in terms of the binary definitions, male and female? Of course now we do define a lot more gender definitions than they did before. So in this case, I would imagine they are thinking more in terms of just those binary terms of male or female. So in that case, could we say, is this a binomial experiment or not?
Yes, because it has two options.
It has two options. So, you're kind of meeting that option number 2 by default if you keep it to just those two options over here. And yes, we are saying, all 4 requirements can be met, which, again, like I said, if we go with today's definitions, then obviously this example would not work. Drawing 5 cards from a deck without replacement and recording whether they are red or black cards. So drawing 5 cards from a deck of cards without replacing them, and then checking out to see if they are red or black cards. Would this be considered a binomial experiment? So you have to have a fixed number of trials. You can only have 2 outcomes. Each outcome has to be independent, and then the probability of success has to remain the same.
I would say yes.
You would say yes? So the reason why, Naomi, it would not work is because you are not replacing the cards. So when you don't replace the cards, you are actually changing the outcome and you are changing the probability. So this one would actually be no, because the cards are not being replaced. Your events are not independent. And this type of example can come with a ball, balls in a box. They do, I think, balls in an urn and just any kind of container. So anytime you are not replacing what you have taken out, it is actually going to change your steps 3 and 4 requirements. So, something to think about. And then part D is saying selecting 5 students from a large school and asking them if they are on the dean's list. So selecting 5 students from a school and asking them if they are on the dean's list. Would this be a binomial experiment? So fixed number of outcomes, fixed number of trials, 2 outcomes, independent events, and the probability of success should remain the same. So asking the students if they are on the dean's list or not.
It would be.
It would be.
The outcomes aren't dependent on the other people's answers, and it's a yes or no question.
Very good. Very nice. Yeah. Sabri, yes. Okay. So yes, this will be satisfying all 4 requirements. And like Dennis said, one person's answer is not going to affect how the other one says, because obviously the idea is you wouldn't be asking all 5 of them at the same time. Recording the number of children in 50 randomly selected families. So you've selected randomly 50 different families and you're recording the number of children. Would this be a binomial experiment? So fixed number of trials, only 2 outcomes, independent events, and the rate of success should remain the same. What do we think?
Would it be no because like the outcomes? I mean,
Yeah,
that-
because you don't know
curious.
how many kids they will have, right? So they could have no kids, they could have, 7, 8 kids in there. So each family would have a different number of kids. So you really wouldn't be able to break it down into two outcomes. Yeah, very nice, Naomi. So, again, you have to meet all four. It's not like, meet one or two of the requirements and you are good. You have to meet all four of those requirements for it to be considered a binomial experiment. So just something to kind of think about as you are going through your homework assignments and your examples. So this one is saying the outcomes of a binomial experiment and the corresponding probabilities for those outcomes is what we would form as your binomial distribution. So some of those requirements are still going to be the same. Your probabilities have to stay between 0 and 1. They can be 0 or equal to 1. And then, of course, all your probabilities have to add up to a total of 1. So all of those requirements will stay. They're just talking about some notation over here for your binomial distribution. This is the binomial distribution formula. Your textbook writes it a little bit differently. So this is, the NCR is this first one over here, which I guess for your textbook, I think they use N and X as those. Then you do P to the power of X. And then instead of Q, they actually use 1 minus P and minus X as your formula, because that's how we define Q, is 1 minus P. And your other older textbook, that's how they defined it. Your current textbook just leaves it as 1 minus P. And this formula I have included in your flip a coin template Google Sheet. So you will see that formula in there. So you have to use this formula to actually calculate your binomial probability. So it's not based on, how we did over here in this part where you looked at how many outcomes your sample space had, and then based on that, you came up with your probability. For these ones over here, you do have to use this formula to come up with your probabilities for each one of them. So this one over here is kind of going back to that tossing a coin 3 times, or, tossing 3 coins at the same time, however you want to look at this. We know this is our sample space over here. They're kind of going through the different requirements for the binomial distribution. So here we wanted to know what is the probability that we will land up with 2 heads. So, in this case, we are doing our NCR, combination formula over here. And in this case, because we know you can get a total of 3 heads, that's our maximum number of trials that you are doing. So you were tossing the coin 3 times. So our N value was going to be 3. We're talking about only 2 outcomes because we know the coin can land on a head or a tail. Of course, we know that one coin toss is not going to affect the other one. So we know our events are independent. And the probability of success, which means in this case, landing on a head, well, you can only get a head or a tail. So that's 1 out of 2. So you can see all 4 of those requirements are being met. So number of trials is 3. That's your N value. We are looking for how many heads can we get, and we were interested in finding the probability for 2 heads. So that's our X value. The probability of landing on a head is 1/2. Again, remember Q is the same thing as 1 minus P. So if the probability of P is 1/2, 1 minus P will also come out to be 1/2. So that's the Q value there. Put it in this little formula over here, and then calculate your binomial probability, and you can see it comes out to be 3/8 or 0.375. And they get into a little bit of discussion about this formula over here, so you can kind of look through that if you want. Let's see. They actually also talk about how you can use the table for the binomial probability distribution. And this is another comparison you guys are doing in your flip a coin assignment. So once you have tossed your coins, and had your probability distribution table designed, after that you will actually be using this table to confirm that all the answers you got by looking at the formula are the same answers you're getting from the table also. And then, yeah, let's talk about how the formula for mean, variance, and standard deviation changes when you are looking at binomial distribution. So we talked about these formulas over here from, just a discrete probability distribution. You had x times px for the mean, and then add all of that together. For our variance, we had x squared times px, add all of them together, and then subtract the square of the mean from it. Well, look how different the formulas are when we are specifically talking about, binomial distribution. For your mean, you are literally multiplying n times p. So that is, your number of trials. How many times did you perform, the experiment? And then what is the probability? Variance is n times p times q, which again in your textbook would be n times p times 1 minus p, and then take its square root to get your standard deviation. So you can see again, just as an example, we're talking about tossing a coin 4 times, which means our number of trials is 4. We're still tossing a coin, so you can either land on a head or a tail. So your probability is going to be 1/2. And then for the 1 minus p will also come out to be 1/2. So the mean is just n times p. 4 times 1/2 is 2. Variance is n times p times q. So you're literally taking that 4 times 1/2, which we already know comes out to be a 2. Multiply that with another 1/2, which gives you an answer of 1. And then take a square root on that, and you get your standard deviation. So very, very straightforward when it comes to calculating your mean, variance, and standard deviation. Let's take a look at this example here. The source book of criminal justice statistics states that 65% of Americans favor sentencing drunk drivers to jail even if they have not caused an accident. So we are saying if a random number of 1,000 individuals is selected, find the mean, variance, and standard deviation. So of course, if you're selecting a random number of 1,000 people, that's going to be your n value. We've got our probability from here, for the people who are in favor of sentencing drunk drivers to jail. So that's your 0.65 for the p value. To calculate our q, which is the 1 minus p, you of course just do 1 minus 0.65, which will end up giving us, what is that, 0.35. So multiply n times p, 1,000 times 0.65, and that's a mean value of 650. N times p times 1 minus p, 1,000 times 0.65, 0.35, you can see that comes out to be 227.5, and take a square root on that, and you've got your standard deviation. So we're basically saying approximately 650 people feel that drunk drivers should be sentenced to jail even if they haven't caused an accident out of this random sample of 1,000 people they selected. And then you have a standard deviation of 15.083. So you can round it to 15 if we're talking about number of people. So you can say give or take 15 people, depending on if you're doing 1 standard deviation, 2 standard deviation, or 3 standard deviation. So again, you can just see the process that's involved when you're working with binomial experiments in this case. And of course, guys, here our 2 outcomes would be people are in favor of sentencing drunk drivers to jail, or people are not in favor of sentencing drunk drivers to jail. So those would be the 2 outcomes that we would be looking for in this case. So these would be the formulas that you will be using in that flip a coin assignment. Did I guess I didn't open it up, but let me just show you that very quickly. So you will see once you get past the experiments and stuff right over here, I've got listed that you will be calculating the mean and the standard deviations, and those are coming from, if you look at your textbook pages, the x times px and x squared times px minus the mean squared. These are the formulas that we saw, coming from this section over here. So this is actually section 6.1 in your textbook for the mean and standard deviation for discrete probability distribution. And then what you're seeing in part B, the n times p and the n times p times 1 minus p. This is coming from section 6.2, and this is specifically for the binomial distribution. So the first one is for discrete probability distribution, and then the second one is specifically for binomial probability distribution. Now, please keep in mind, binomial is also part of the discrete. We're just getting a little bit more specific in that. And then, of course, you're comparing your answers for the two means and the two standard deviations. So again, if you haven't started working on this, you should definitely, go ahead and get started. And in this template for the flip a coin, and of course, you guys worked on this last time, you will see right here at the top, you've got your binomial distribution formula that I was talking about. So this is also coming from your textbook pages over here. So if you look at your textbook, you will see, those same rules, same formulas being listed over here. So here's your mean for discrete. Here's your standard deviation formula, and you will find these in section 6.1. And then in section 6.2 is where we get more specific with the binomial probability distribution. So because, again, one of you had asked me that question about the handout section numbers are different. So just please, again, keep in mind, they're just coming from different books, but the formulas, the information is just the same. Each, author just has a different way of writing down their, formulas. So that was your binomial distribution formula. And then I was showing you your mean and standard deviation formulas over here. So you've got examples in your textbook also. If you want to look at, how they are breaking those down and how they come up with that, you can take a look through those. But this is the last part that you guys will be working on after you finish your homework assignments in my stat lab for chapters 5 and 6. Any questions either on just discrete or binomial probability distribution, or anything on this flip a coin assignment? Sorry, you are also going to be graphing a binomial probability distribution, which will look like these graphs that you see over here. Go ahead.
How do we like show our work in Excel? Is there like a formula that we use, like a function, or no?
I have not used anything specific to binomial distributions. So what I want you to do is actually show me, just using these formulas, what your calculations will come out to be. And I think I said you guys can turn in, well, I guess I'm just having you turn in the Excel or Google Sheets. So you can turn it on the Google Sheets or Excel itself. If you want to turn it in using Word or Google Docs, you can do that also. And if you're doing it on paper, these calculations for mean and standard deviation, then use a scanning app like Qt PDF, I think is one of them. Is it that? I haven't used it in a while, but I think that's one of the PDFs. I know iPhones have a built-in scanner, so if you guys have an iPhone, you can use that. If you are at work and you have one of those copier machines that also does the scan for you, you can do that. The only problem with photographs is if you send me a photograph, sometimes it does not download easily at my end, and so I won't be able to see all your work. So if you scan your document and save it as a PDF file, it actually becomes easier for me to take a look at it. So you can turn in your work through Google or Excel. You can use Word or Google Docs if you're typing it out, or if you're working on it on a piece of paper, then just scan your paper and send me your calculations. So Mary, whichever one of those options works out the best for you. Anybody else have a question on, again, chapter 6 or this assignment in particular? Okay, so remember guys, on Wednesday, like we normally do, during class time, we'll take the chapter chapters 5 and 6 exam. And then by midnight on Wednesday, you will be submitting your flip a coin assignment. So in this template that I had you guys use last time, we've got everybody's data in here. Just keep yours, delete everybody else's. So, if you have done your 3 flip a coin experiments, just save your data. You can get rid of the others because obviously I'm not interested in seeing everybody's in the same sheet. So just save yours. And then on the second page is where you will do your probability distribution. So remember to calculate these P of X values over here is where you are using this formula for the binomial probability distribution. And for the combination part, that NCX part, you can use your built-in functions in your calculator. So you have the NCR key on your calculators. I had also shown you the Desmos calculator. If you want to use Desmos, that's fine. Just go to desmos.com. So you can see that's the spelling DESMOS, desmos.com, and under math tools, just find your scientific calculator. And when you get to the scientific calculator, go under the function option over here, and under functions, you will find that NCR key. So if you don't have a handheld calculator, you can definitely use this Desmos and it will do the calculations for you. And remember, this is in the format of you put the N value first and then the R value, or your textbook is calling it X, doesn't matter. So put those numbers in and it will do the calculations for you. So if you have 4 trials, 2 heads, you can see that's what the number will come out to be. So remember, these tables that you are completing over here, you will be doing those by using the formula. And then once you get these answers, those answers are the ones you will be then comparing with this binomial distribution table over here to try and see, do your answers come out to be the same as what you're seeing in the table, or if they are different, and what's the reason behind it. So you would kind of have to think about, should my answers be the same or should they be different, that kind of thing. So that is also part of the question that you are answering over here. And there's no video that you have to do on Flipgrid. Everything you will be turning in is going to be through Excel and Google Sheets. So you can put your answers right there in the document itself. You don't have to do a separate, video recording or anything like that. And while you're working on this, and if something comes up, please feel free to send me an email. I will have office hours, till 4:30. So if you're working on it then and you want to ask me something, you can. Of course, I'll be available tomorrow and on Wednesday also. Just don't send me anything late Wednesday night, because I'll probably not be, checking my emails late at night. So probably till class time would be a safe bet. Okay. All right, guys. So if you don't have any questions, then I will see you on Wednesday for our chapters 5 and 6 exam. Good luck, everyone. Just make sure you get your 90% on your homework assignments, and see you for our Math 092 on Wednesday afternoon, guys. So be careful. Have a wonderful day, guys, and take care. Stay safe. Bye, guys. Hey, Sabri, Eliana, did you guys have any questions?